In the last video, we were considering this particle, which moves with the velocity that's given. We made a sign chart for velocity and decided that the velocity was positive for times between 0 and pi over 3, and negative for times between pi over 3 and pi over 2, which means the particle's moving to the right between 0 and pi over 3, and moving to the left between pi over 3 and pi over 2. And it's momentarily 0 at the exact moment when time equals pi over 3. So in the next question, the particle's displacement on the given time interval. The time interval is 0 to pi over 2. So displacement is the integral of velocity over the time interval we were given. That's 0 to pi over 2. So displacement is the one that's very straightforward. You just integrate. The positives and negatives are going to cancel out however they will. Whatever the result of the integration is going to be my displacement over that time interval. So I'm going to make a u substitution. I'm going to let u equal 3t. I'm going to let du over 3 equal dt. I'm going to leave my limits off and put them back at the end. Your other option, of course, would be to change to u limits. So this is going to be the integral. I'm going to leave off the limits of 6 times the sine of u times du over 3. The 6 and that 3 are going to cross cancel, and it's going to leave me 2 times the integral of sine u du. The antiderivative of sine of u is negative cosine of u. I'm going to come up here, and so that's negative cosine, oops, that was 2 times negative cosine of, what's u? U was 3t. Evaluated from, since I put my t's back at 0 to pi over 2. So it's going to be 2 times the opposite of cosine of 3 pi over 2. Well, 3 pi over 2, 0. Minus 2 times the opposite of cosine of 3 times 0 is 0. The opposite of cosine of 0, opposite of 1. So it's 2 times 0 is 0 plus 2. The displacement is 2. And what is the particle's final position? We said the particle's final position is initial position. We've been told is 3. So let's label this. That was displacement. Displacement is the result of that integral, which is 2. And the final position, which I would call x of pi over 2. Notice I've been told that x is my position function. And I know x of 0 is 3. That means I was at position 3 when I started, and I got 2 extra spaces. So that's going to be 3 plus 2 equals 5. The final position, 5. So the total distance traveled by the particle is going to be slightly different. I have to pretend the particle's wearing a pedometer. I want to figure out how far it travels on that time for the moments when it's moving forward. And then separately, I want to add in the distance it travels for all the times that it's moving backwards. So I have to go back to that thing that I did in part A, which is figure out that the velocity is positive between 0 and pi over 3. The velocity is negative between pi over 3 and pi over 2. So total distance traveled, that is not an approved abbreviation, but I'm going to not write out total distance traveled. That's going to be the integral. If it's a calculator section on the AP test, feel free to write this expression. That's the absolute value of v of t dt. And if you were able to type the velocity function into your calculator inside the integral, inside the absolute value bars, inside the integral, you will get the correct answer. And this isn't a calculator active scenario. So it's my job to figure out how to compute the area under the absolute value of the velocity curve. And that's by splitting up my integral. This would have been the whole interval 0 to pi over 2. splitting it up. I know the velocity is already positive on 0 to pi over 3. So I don't have to worry about finding the absolute value. And I know the velocity is negative on, that's supposed to be pi over 3, on the interval from pi over 3 to pi over 2. So what I'm going to do is I can take that whole integral, whatever this section is, it's going to be some area under the curve, and that whole area is going to be negative. So at the end, I'm going to take the absolute value of that whole section and add it to the positive area that I get for the first section. So that's going to be the integral from 0 to pi over 3 of, I made that u substitution. Oh, I made the u substitution, so I know my antiderivative already. I can even do this. What was my antiderivative? It was 2 times the opposite of cosine of 3t. I'm going to evaluate that from 0 to pi over 3. I'm going to add the absolute value of whatever I get when I use that same antiderivative, negative cosine of 3t. Well, evaluated from pi over 3 to pi over 2. Alright, so here I go. That's going to be 2 cosine of pi over 3, 2 times the opposite of the cosine of 3t, when t is pi over 3, is pi. Cosine of pi is -1. Minus 2 times the opposite of cosine of 0 is -1. No, cosine of 0 is +1. I have the negative in there already. Plus, this part, it's going to end up being a negative answer, so I'm going to have to put it in absolute value bars. 2 times the cosine of, I'm going to put pi over 2 in for t, that's 3 pi over 2. The cosine of pi over 2, 3 pi over 2 is 0, so 2 times the opposite of 0 minus 2 times the opposite of -1. I just did that one a second ago. Right, that's the same as this. Okay, so what do I have here? I have 2 times the opposite of 1 is 2, plus 2 times the opposite of 1 is 2, plus the opposite, so the absolute value of, that's going to be 0 minus 2. So that turns into, this 2 plus 2 makes 4, plus the absolute value of -2 makes a +2, which makes 6. Total distance traveled is 6. We can think of Chapter 7 as sort of the Chapter 4 of Semester 2. So in Chapter 3 you learned all about how to find derivatives, and in Chapter 4 we're like, oh, now that I know how to find derivatives, here's some kinds of problems I can solve with them. So in Chapters 5 and 6 we found out all different ways we can find antiderivatives and evaluate integrals. And in Chapter 7, now that we know how to evaluate integrals, Chapter 7 introduces this whole big set of problems that we can solve using an integral. That's why one of your standards is use integrals to solve problems. So Chapter 5 and 6 stuff is all about how to evaluate the integral once you can write it. But Chapter 7, we're going to have to write our own integrals. So remember that integrals are just a way of implying, of saying that I want to add up the areas of infinitely many rectangles, or add up the sums of infinitely many products of 2 or more things. So if I can think about the quantity I'm looking for as the sum of infinitely many very small products, then I can write an integral, and then I can use everything I learned in Chapter 5 and 6 to evaluate it. So, right, so this is basically what I just said in 3 steps, if that is helpful. Take a look at example 5 from your textbook. I'm going to move me out of the way. What if I knew that the rate of potato consumption was this, given by C of t, and that's measured in millions of bushels of potatoes per year, and t is measured in years since the beginning of 1970. Can I figure out how many bushels of potatoes got consumed in that country between the beginning of 1972 and the end of 1973? So what do I have to think about? Remember, we said in chapter 6 that we could use areas not just under velocity curve. So area under velocity curve gives distance traveled, because distance traveled is the antiderivative of velocity. So, and actually better, because velocity is the derivative of position or distance traveled. So we want to think about this. This C of t function I have is the derivative of it. It's the rate of change of the amount of potatoes eaten. So if I can integrate C, I'm going to get the number of potatoes eaten. So another way to think about it, if this function C of t is measured in millions of bushels of potatoes per year, and I would want to multiply it by a time to get how many bushels were consumed over that time. I would wish that it were a constant function. If this were like 5 million bushels per year, I would just multiply the number of years by 5. But my C of t actually changes with time, so that means I have to break up my multiplications into infinitely tiny chunks, the same way I had to break up my velocity function into infinitely tiny chunks and multiply miles per hour times a teeny tiny change in the hours. So this is the integral I want to write. I want to that's not the whiteboard function. Here's the whiteboard. I want to integrate C of t times a very small change in time, which I'm going to call dt. My only other job is to figure out what my limits are going to be. So if 0 is the beginning of 1970, then 1 is the beginning of 1971, and 2 times 2 is the beginning of 1972. And I want to go to the end of 1973, which occurs simultaneously with the very beginning of 1974. So that's going to be time 4. So this is the expression I would write on the free response section of the AP test. And I would type into my calculator the integral from 2 to 4 of 2.2 plus 1.1 to the t. It should all go in parentheses times dt. And I'll evaluate in that 1 second. So that gives us the answer 7.066, but remember, our C function was measured in millions of bushels per year, so that is 7.066 million bushels. A lot of potato.